What if the universe is hiding something from us? Something so vast and mysterious that it makes up most of the energy in existence, yet we can't see it, touch it, or even fully understand it. This isn't science fiction, it's one of the greatest mysteries of modern science. Scientists call it the universe's missing energy, and it's a puzzle that has baffled the brightest minds for decades. Where is this energy? What is it made of? And why does it seem to be slipping through our fingers? In this video, we're diving into 30 mind-blowing theories that attempt to unravel this cosmic enigma. From the invisible grip of dark matter to the strange forces of dark energy, and even wild ideas like extra dimensions and cosmic strings, we'll explore the most fascinating explanations scientists have come up with. Whether you're a space enthusiast or just curious about the mysteries of the cosmos, this journey will challenge everything you thought you knew about the universe. So, are you ready to uncover the secrets of the universe's missing energy? Let's dive in and explore the theories that could change the way we see the cosmos forever. Now, let's turn our attention to the first and perhaps most widely discussed theory, the dark matter hypothesis. Imagine a universe where most of the matter is invisible, yet its presence is felt everywhere. That's the essence of dark matter. Scientists believe this mysterious substance makes up about 27% of the universe's total mass and energy, yet it doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes, but its gravitational effects are undeniable. So, how do we know dark matter exists? It all comes down to gravity. When astronomers observe galaxies, they notice something strange. Stars on the outer edges of galaxies move faster than they should based on the visible matter alone. This suggests there's an unseen force, an invisible mass pulling on them. That's where dark matter comes in. It acts like a cosmic glue, holding galaxies together and shaping the large-scale structure of the universe. But what exactly is dark matter made of? That's the million-dollar question. While we don't know for sure, scientists have proposed several candidates, such as weakly interacting massive particles or WIMP. These hypothetical particles barely interact with ordinary matter, making them incredibly difficult to detect. Despite decades of searching, dark matter remains elusive, but its gravitational fingerprints are everywhere, from the rotation of galaxies to the bending of light around massive objects, a phenomenon known as gravitational lensing. The dark matter hypothesis isn't just a wild guess, it's supported by a mountain of evidence. Without it, our understanding of the universe's structure and evolution would fall apart. Yet, for all its importance, dark matter remains one of the greatest unsolved mysteries in science. Could it be the key to unlocking the universe's missing energy? Only time and more research will tell. Next, we'll explore another fascinating theory, dark energy, the mysterious force driving the universe's accelerated expansion. Stay tuned as we uncover how this invisible energy might be shaping the fate of the cosmos. Now, let's shift our focus to another groundbreaking theory that could hold the key to the universe's missing energy, dark energy. Unlike dark matter, which pulls things together through gravity, dark energy is thought to be a mysterious force pushing the universe apart at an ever-increasing rate. This discovery, made in the late 1990s, completely changed our understanding of the cosmos. So, what exactly is dark energy? Think of it as the opposite of gravity. While gravity pulls objects toward each other, dark energy seems to be doing the opposite, stretching the fabric of space itself. Scientists estimate that dark energy makes up about 68% of the universe's total energy content, making it the dominant force shaping the universe's fate. But here's the catch: we have no idea what it actually is. The evidence for dark energy comes from observations of distant supernovae, the explosive deaths of massive stars. Astronomers noticed that these supernovae were dimmer than expected, suggesting they were farther away than they should be. This could only mean one thing: the universe isn't just expanding, it's accelerating. And dark energy is the leading explanation for why this is happening. But how does dark energy differ from dark matter? While both are invisible and mysterious, they play very different roles. Dark matter acts like a cosmic scaffold, holding galaxies and galaxy clusters together through its gravitational pull. Dark energy, on the other hand, is more like a cosmic repellent, pushing everything apart and driving the universe's expansion. Together, these two invisible forces make up about 95% of the universe's total energy and matter, leaving just 5% for everything we can actually see: stars, planets, and us. The implications of dark energy are profound. If it continues to dominate, the universe could keep expanding faster and faster, eventually leading to a scenario where galaxies are so far apart that the night sky becomes empty and dark. This raises a critical question. Could dark energy be the missing piece of the puzzle when it comes to the universe's energy budget? As we continue to explore this enigmatic force, one thing is clear: dark energy challenges our understanding of physics and the very nature of reality. Could it be a property of space itself, or is it something entirely new? The answers remain hidden, but the search for them is reshaping our view of the cosmos. Next, we'll dive into another intriguing possibility: quantum vacuum energy, and how the seemingly empty space around us might hold the key to the universe's missing energy. Stay with us as we uncover the secrets of the quantum realm. Now, let's venture into the strange and fascinating world of quantum vacuum energy. At first glance, the idea that empty space could contain energy might sound like science fiction, but according to quantum mechanics, it's a very real possibility. In fact, the vacuum of space isn't truly empty, it's teeming with activity at the smallest scales, and this activity might hold the key to understanding the universe's missing energy. Quantum vacuum energy arises from the principles of quantum mechanics, which tell us that even in a perfect vacuum, particles and their antimatter counterparts constantly pop in and out of existence. These fleeting particles, known as virtual particles, create a kind of background energy that permeates all of space. This energy is often referred to as zero-point energy because it exists even at absolute zero, the coldest possible temperature where all classical motion stops. But here's where things get interesting. If empty space is filled with this energy, why don't we notice it? The answer lies in the challenges of measuring it. Quantum vacuum energy is incredibly subtle, and its effects are usually only detectable on the tiniest scales. However, when scientists try to calculate how much energy this vacuum might contain, they run into a problem. The numbers they get are astronomically large, far larger than what we observe in the universe. This discrepancy is known as the vacuum catastrophe, and it's one of the biggest unsolved puzzles in physics. So, how does quantum vacuum energy connect to the universe's missing energy? Some theories suggest that this energy could be a form of dark energy, driving the accelerated expansion of the universe. Others propose that it might interact with gravity in ways we don't yet understand, potentially accounting for the missing energy in cosmological models. However, the challenge lies in reconciling the enormous theoretical predictions with the relatively small effects we observe in the cosmos. Measuring quantum vacuum energy is no easy task. Unlike dark matter or dark energy, which leave indirect traces through their gravitational effects, vacuum energy is far more elusive. Scientists have attempted to detect it through experiments like the Casimir effect, where two uncharged metal plates placed very close together experience a tiny force due to the quantum fluctuations between them. While this effect confirms the existence of vacuum energy, it's still a far cry from explaining its role in the universe's energy budget. As we continue to explore this mysterious energy, one thing is certain: quantum vacuum energy challenges our understanding of the universe at its most fundamental level. Could it be the missing piece of the puzzle, or is it just another clue in a much larger mystery? The answers remain hidden, but the search for them is pushing the boundaries of science and technology. Next, we'll turn our attention to another intriguing theory, modified Newtonian dynamics, or MOND, and how it offers an alternative explanation for the universe's missing energy without invoking dark matter. Stay with us as we explore this bold reimagining of gravity itself. Now, let's shift gears and explore a theory that challenges one of the most fundamental laws of physics, modified Newtonian dynamics, or MOND. Unlike the theories we've discussed so far, which rely on mysterious substances like dark matter or dark energy, MOND takes a completely different approach. It suggests that the missing energy problem might not be about something we can't see, but rather about something we thought we already understood: gravity itself. At its core, MOND proposes that Newton's laws of gravity, which have been the foundation of physics for centuries, might need a tweak when it comes to the vast scales of the universe. According to Newton, gravity weakens with distance, following a simple inverse square law. This works perfectly for explaining the motion of planets in our solar system or the way objects fall to the ground. But when we look at galaxies and their rotation, something doesn't add up. Stars on the outer edges of galaxies move faster than Newton's laws predict, as if there's an invisible force at play. This is where MOND steps in. Instead of invoking dark matter to explain this discrepancy, MOND suggests that gravity behaves differently at extremely low accelerations like those found in the outer regions of galaxies. In these conditions, gravity might not follow the inverse square law as strictly as we thought. Instead, it could become stronger, providing the extra pull needed to account for the observed motion of stars without requiring any unseen matter. The idea of modifying gravity isn't new, but MOND has gained attention because it successfully explains the rotation curves of many galaxies without needing dark matter. It's a bold reimagining of one of physics' most trusted laws, and it raises an intriguing question. What if the missing energy isn't missing at all, but simply a result of our incomplete understanding of gravity? However, MOND isn't without its challenges. While it works well for galaxies, it struggles to explain other phenomena, like the behavior of galaxy clusters or the cosmic microwave background, where dark matter seems to play a crucial role. This has led some scientists to propose hybrid models combining elements of MOND with dark matter, while others continue to refine the theory to address these gaps. What makes MOND so fascinating is its simplicity. Instead of introducing new, unseen components to the universe, it asks us to reconsider what we already know. Could gravity truly be more complex than we've imagined, or is dark matter still the more likely explanation? The debate continues, and as we gather more data from telescopes and experiments, we may inch closer to an answer. As we move forward, we'll dive into another captivating idea: cosmic strings, and how these one-dimensional defects in space-time might hold clues to the universe's missing energy. Stay tuned as we unravel this cosmic mystery further. Now, let's turn our attention to a concept that sounds like it's straight out of science fiction, but is deeply rooted in theoretical physics: cosmic strings. These are one-dimensional defects in space-time, often described as incredibly thin, ultra-dense filaments stretching across the universe. Imagine them as cracks or wrinkles in the fabric of reality, remnants from the earliest moments after the Big Bang. But how could these cosmic strings help explain the universe's missing energy? Let's unravel this intriguing idea. Cosmic strings are thought to have formed during a phase transition in the early universe, much like cracks forming in ice as water freezes. As the universe cooled and expanded, certain symmetries in the laws of physics were broken, creating these defects. Unlike black holes or stars, cosmic strings are not made of matter but are instead pure energy, twisted into a thread-like structure. They're incredibly thin, thinner than an atom, but staggeringly dense, with a single cosmic string potentially weighing as much as an entire galaxy. So, how do cosmic strings tie into the missing energy problem? One possibility is that their immense gravitational influence could affect the distribution of matter and energy in the universe. As these strings move through space, they could create ripples in space-time, distorting the paths of light and matter around them. This gravitational lensing effect might help explain some of the anomalies we observe in the cosmos, such as the unexpected clustering of galaxies or the uneven distribution of cosmic microwave background radiation. Another fascinating aspect of cosmic strings is their potential to carry energy across vast distances. If they exist, they could act as cosmic highways, transporting energy from one part of the universe to another. This could mean that some of the energy we perceive as missing might simply be hidden within these strings, redistributed in ways we don't yet fully understand. But how do we know if cosmic strings are real? While they haven't been directly observed, there are tantalizing hints that they might exist. For example, some scientists have proposed that the faint, unexplained signals detected in gravitational wave observatories could be the result of cosmic strings vibrating or colliding. Additionally, their gravitational effects might leave subtle imprints on the cosmic microwave background, which future telescopes could potentially detect. The idea of cosmic strings is both captivating and speculative. They challenge our understanding of space-time and energy, offering a unique perspective on the universe's mysteries. While they remain theoretical for now, their potential to explain the missing energy problem keeps them at the forefront of cosmological research. As we continue our journey through these theories, we'll next explore another mind-bending concept: the possibility of extra dimensions and how they might hold the key to the universe's missing energy. Stay with us as we dive deeper into the cosmic unknown. Now, let's stretch our imaginations even further as we venture into the realm of extra dimensions. What if the universe we see with its three spatial dimensions of length, width, and height is just the tip of the iceberg? What if there are hidden dimensions curled up or extending beyond our perception that hold the key to the universe's missing energy? This idea, while sounding like something from a sci-fi novel, is a serious area of study in theoretical physics, and it could revolutionize our understanding of reality. The concept of extra dimensions isn't entirely new. In fact, it dates back to the early 20th century when physicists like Theodore Kaluza and Klein proposed that our universe might have more than the three spatial dimensions we're familiar with. Their work suggested that these extra dimensions could be incredibly tiny, curled up so tightly that they're invisible to us, yet they might still influence the fundamental forces of nature, including gravity. So, how do extra dimensions tie into the missing energy problem? One possibility is that some of the energy we're searching for might be leaking into these hidden dimensions. Imagine our universe as a three-dimensional sheet floating in a higher dimensional space. Energy could flow between our observable universe and these extra dimensions, making it seem like energy is disappearing from our perspective. This could explain why our measurements of the universe's total energy don't add up, because we're only accounting for the energy in the dimensions we can see. Another intriguing idea is that these extra dimensions could house entirely new forms of energy or particles that we haven't yet detected. For example, some theories suggest that gravity, which is much weaker than the other fundamental forces, might actually be stronger in these extra dimensions. If that's the case, then the gravitational energy we observe in our three-dimensional world might just be a fraction of what's actually out there, with the rest hidden in these unseen realms. But how do we test such a mind-bending idea? While we can't directly observe extra dimensions, scientists have proposed ways to detect their effects. For instance, experiments at particle colliders like the Large Hadron Collider are searching for evidence of higher dimensional particles or energy signatures. Additionally, precise measurements of gravitational waves or the behavior of black holes could reveal subtle hints of extra dimensions influencing our universe. The idea of extra dimensions challenges our everyday understanding of space and reality, but it also opens up exciting possibilities for solving some of the universe's greatest mysteries. As we continue to explore these theories, we'll next dive into the holographic principle, a concept that suggests our entire universe might be encoded on a two-dimensional surface. Stay with us as we peel back another layer of the cosmic unknown. Now, let's take a step into a concept that feels like it's straight out of a futuristic sci-fi movie, the holographic principle. Imagine this: what if everything we see, touch, and experience in our three-dimensional universe is actually encoded on a two-dimensional surface, like a cosmic projection? This mind-blowing idea isn't just a wild thought experiment. It's a serious theory in physics that could help explain the mystery of the universe's missing energy. The holographic principle suggests that all the information about our universe, every star, every planet, every particle, might be stored on a two-dimensional boundary, much like how a hologram encodes a 3D image on a flat surface. This means that the three-dimensional world we perceive could be a kind of illusion, with the real data of the universe existing on a lower dimensional plane. So, how does this tie into the missing energy problem? If the universe's energy and information are encoded on a two-dimensional surface, it's possible that some of the energy we're missing in our three-dimensional calculations is actually hidden in this lower dimensional framework. In other words, the energy might not be missing at all. It could just be stored in a way that's invisible to our current methods of measurement. This idea comes from the study of black holes, where physicists discovered that the information about everything that falls into a black hole is somehow preserved on its two-dimensional event horizon. This led to the broader idea that the entire universe might operate in a similar way, with all its information and energy encoded on a vast two-dimensional surface. But how could this work in practice? Think of it like a movie projected onto a screen. The movie appears three-dimensional with depth and movement, but it's actually created from flat, two-dimensional data. Similarly, our universe might be a projection from a two-dimensional source code, with the energy we perceive being just a fraction of what's actually stored in this underlying framework. Testing the holographic principle is no easy task, but scientists are exploring ways to detect its effects. For example, precise measurements of cosmic microwave background radiation. The afterglow of the Big Bang could reveal subtle patterns that hint at a two-dimensional origin. Additionally, experiments in quantum gravity and string theory are providing clues about how such a principle might operate in reality. The holographic principle challenges our understanding of space, energy, and reality itself, but it also offers a fascinating new perspective on the universe's missing energy. As we continue to explore this idea, we'll next turn our attention to phantom energy, a hypothetical form of dark energy with some truly bizarre properties. Stay tuned as we unravel another layer of this cosmic puzzle. Now, let's shift our focus to something even more mysterious: phantom energy. This hypothetical form of dark energy takes the concept of dark energy to an entirely new level, and it might just hold the key to understanding the universe's missing energy. Phantom energy is a theoretical idea that suggests dark energy could have a property called negative pressure. Unlike regular energy, which pushes outward and drives the expansion of the universe, phantom energy's negative pressure would actually increase over time. This means it wouldn't just accelerate the expansion of the universe, it would do so at an ever-increasing rate. Here's where it gets even stranger. If phantom energy exists, it could lead to a scenario known as the Big Rip. In this dramatic endgame, the universe's expansion would become so rapid that it would eventually tear apart galaxies, stars, planets, and even atoms themselves. While this might sound like the plot of a cosmic horror story, it's a serious possibility that physicists have explored to explain the universe's missing energy. So, how does phantom energy tie into the missing energy problem? If phantom energy is real, it could account for the energy we can't detect in our current observations. Its unusual properties might mean that it interacts with the universe in ways we don't yet understand, effectively hiding energy from our measurements. This could explain why our calculations of the universe's total energy don't add up. Phantom energy might be the missing piece of the puzzle. But why would phantom energy have such extreme effects? The answer lies in its negative pressure. In physics, pressure isn't just about pushing or pulling. It's also about how energy interacts with space itself. Phantom energy's negative pressure would create a kind of repulsive force that grows stronger as the universe expands, leading to the runaway acceleration we've observed. Testing the existence of phantom energy is incredibly challenging, but scientists are looking for clues in the behavior of distant supernova and the large-scale structure of the universe. By studying how the universe expands over time, they hope to find evidence of this elusive energy and its bizarre properties. Phantom energy pushes the boundaries of our understanding of the cosmos, offering a radical explanation for the universe's missing energy and its accelerated expansion. As we continue to explore this idea, we'll next turn our attention to quintessence, another fascinating theory that offers a different perspective on dark energy and the mysteries of the universe. Stay with us as we dive deeper into the cosmic unknown. Now, let's explore another intriguing possibility: quintessence. Unlike phantom energy, which suggests a runaway expansion of the universe, quintessence offers a more subtle and dynamic explanation for dark energy and the universe's missing energy. Quintessence is a theoretical concept that proposes dark energy isn't a constant force but rather a dynamic field that changes over time and space. Imagine it as a kind of cosmic fluid that permeates the universe, influencing its expansion in ways that vary depending on where and when you look. This idea stands in contrast to the traditional view of dark energy as a fixed, unchanging entity. So, how does quintessence work? Think of it like this. If dark energy is a steady push, quintessence is more like a push that can grow stronger or weaker depending on the conditions. This variability means that quintessence could explain why the universe's expansion seems to be accelerating at different rates over time. It's a flexible theory that adapts to the observations we've made, offering a more nuanced explanation for the missing energy problem. One of the most fascinating aspects of quintessence is its connection to the early universe. Some scientists believe that quintessence might have played a role in cosmic inflation, the rapid expansion of the universe just after the Big Bang. If true, this would mean that quintessence isn't just a modern phenomenon but something that has shaped the universe from its very beginnings. But how do we test this idea? Unlike phantom energy, which predicts extreme outcomes like the Big Rip, quintessence is harder to pin down because of its dynamic nature. Researchers are looking for clues in the cosmic microwave background, the faint afterglow of the Big Bang, as well as in the distribution of galaxies across the universe. By studying these patterns, they hope to find evidence of quintessence's influence on the cosmos. Quintessence also raises an interesting question. Could it be related to other fundamental forces in the universe? Some theories suggest that quintessence might interact with gravity or even with particles we haven't yet discovered. This opens up a whole new realm of possibilities for understanding not just dark energy but the very fabric of reality itself. As we continue to unravel the mysteries of the universe, quintessence stands out as a compelling alternative to the more extreme theories of dark energy. It's a reminder that the cosmos is full of surprises, and that the answers to our biggest questions might lie in the subtle, ever-changing forces that shape the universe. Next, we'll turn our attention to the Chaplygin gas model, a theory that takes a completely different approach by unifying dark matter and dark energy into a single, elegant framework. Stay with us as we dive deeper into the cosmic puzzle. Now, let's shift our focus to a theory that takes a bold step in simplifying the cosmic puzzle, the Chaplygin gas model. This idea proposes something truly fascinating. What if dark matter and dark energy aren't separate entities at all, but instead two sides of the same cosmic coin? The Chaplygin gas model suggests that both could be unified into a single, exotic fluid that behaves differently depending on the conditions of the universe. Here's how it works. Imagine a fluid that starts out behaving like dark matter in the early universe, clumping together to form the large-scale structures we see today, like galaxies and galaxy clusters. But as the universe expands, this same fluid begins to act more like dark energy, driving the accelerated expansion we observe now. It's a seamless transition from one role to another, all within the same framework. What makes the Chaplygin gas model so appealing is its elegance. Instead of needing two separate explanations for dark matter and dark energy, this theory offers a single, unified solution. It's like finding out that two mysterious characters in a story are actually the same person, just playing different roles at different times. But how does this help us solve the missing energy problem? By combining dark matter and dark energy into one fluid, the Chaplygin gas model provides a way to account for the universe's energy budget without introducing additional unknowns. It's a streamlined approach that could potentially explain why the universe behaves the way it does, from its early formation to its current accelerated expansion. Of course, like any theory, the Chaplygin gas model has its challenges. One of the biggest hurdles is figuring out how to test it. Since it proposes a fluid that changes its behavior over time, scientists need to find ways to observe its effects across different eras of the universe. This could involve studying the distribution of galaxies, the cosmic microwave background, or even the way light bends around massive objects, a phenomenon known as gravitational lensing. Despite these challenges, the Chaplygin gas model remains a compelling contender in the search for answers to the universe's missing energy. It's a reminder that sometimes the most elegant solutions come from thinking outside the box and looking for connections where others see only separation. As we move forward, we'll explore another intriguing idea, brain cosmology, which takes us into the realm of higher dimensions and alternate realities. Stay tuned as we continue to unravel the mysteries of the cosmos. Now, let's venture into a theory that takes us beyond the familiar three dimensions of space and into the realm of higher dimensions, brain cosmology. This idea, rooted in string theory, suggests that our universe might not be all there is. Instead, it could be a kind of membrane or brain floating in a higher dimensional space. Imagine our universe as a sheet of paper drifting in a vast, unseen ocean. That sheet is our brain, and the ocean represents the higher dimensional space it inhabits. So, how does this tie into the missing energy problem? According to brain cosmology, the energy we can't account for in our universe might be leaking into these extra dimensions. Think of it like water seeping through a sponge. Some of the universe's energy could be escaping into these hidden dimensions, making it appear as though energy is missing when, in reality, it's just flowing somewhere we can't see. This theory also opens up fascinating possibilities for gravity. In brain cosmology, gravity might be the only force that can travel between dimensions, which could explain why it feels so weak compared to the other fundamental forces. If gravity is spreading out into these extra dimensions, it would dilute its strength in our observable universe, potentially accounting for some of the discrepancies in our energy calculations. But what's truly mind-bending about brain cosmology is the idea that there could be other brains, other universes floating alongside ours in this higher dimensional space. These parallel universes might be just out of reach, yet their presence could influence our own universe in subtle ways. For instance, collisions between brains could have triggered events like the Big Bang, reshaping our understanding of how the universe began. Of course, brain cosmology isn't without its challenges. One of the biggest hurdles is figuring out how to test these ideas. Since we can't directly observe higher dimensions or other brains, scientists have to rely on indirect evidence, such as anomalies in gravitational waves or the behavior of particles in high-energy experiments. Despite these challenges, brain cosmology offers a bold and imaginative way to tackle the mystery of the universe's missing energy. It reminds us that sometimes the answers we seek might lie in places we can't yet see or fully comprehend. As we continue our journey, we'll explore another intriguing possibility, the idea that the speed of light might not always have been constant, and how this could play a role in the missing energy puzzle. Stay with us as we dive deeper into the cosmos and uncover more of its secrets. Now, let's shift our focus to a theory that challenges one of the most fundamental constants in physics, the speed of light. What if the speed of light wasn't always constant? What if it changed over time, especially in the early universe? This idea, known as the variable speed of light theory, is both controversial and fascinating, offering a potential explanation for the universe's missing energy. According to this theory, the speed of light might have been much faster in the early moments of the universe, right after the Big Bang. If that's the case, it could have had profound effects on how energy was distributed and how the universe evolved. For instance, a faster speed of light in the early universe could have allowed energy to spread out more quickly, potentially leaving behind regions where energy appears to be missing today. This idea also ties into the concept of inflation, the rapid expansion of the universe shortly after the Big Bang. If the speed of light was variable, it could have influenced the rate of inflation, altering the way energy was distributed across the cosmos. Some scientists suggest that this variability might explain why our current measurements of the universe's energy don't quite add up. But why would the speed of light change? One possibility is that the laws of physics themselves were different in the early universe. In those extreme conditions, with temperatures and densities far beyond anything we can recreate today, the fundamental constants we take for granted might have behaved differently. The speed of light in this scenario could have been a dynamic value, adjusting as the universe cooled and expanded. Of course, this theory isn't without its critics. The speed of light is a cornerstone of modern physics, and altering it raises significant questions about the consistency of the laws of nature. Critics argue that if the speed of light were variable, it would leave observable traces in the cosmic microwave background radiation or in the behavior of distant galaxies. So far, such evidence has been elusive, but that hasn't stopped scientists from exploring the idea. Supporters of the variable speed of light theory point to its potential to solve multiple cosmological puzzles, not just the missing energy problem. For example, it could help explain the uniformity of the cosmic microwave background or the fine-tuning of the universe's initial conditions. While it remains a speculative idea, it's a reminder that sometimes the answers to the universe's biggest mysteries might require us to rethink even the most basic assumptions. As we continue our exploration, we'll turn our attention to another intriguing concept, entropic gravity, a theory that links gravity to entropy and information, and how it might provide an alternative explanation for missing energy. Stay with us as we uncover more layers of this cosmic mystery. Now, let's dive into a theory that flips our understanding of gravity on its head: entropic gravity. This idea suggests that gravity isn't a fundamental force in the traditional sense, but rather an emergent phenomenon, arising from the behavior of entropy and information in the universe. It's a radical departure from how we've thought about gravity since the days of Newton and Einstein, and it might just hold the key to explaining the universe's missing energy. At its core, entropic gravity proposes that gravity is a consequence of the way information is distributed and processed in the cosmos. Think of it like this: the universe is like a vast, interconnected network, and gravity emerges from the way this network organizes itself. This theory draws heavily from the concept of entropy, which is a measure of disorder or randomness in a system. In simple terms, entropic gravity suggests that the force we experience as gravity is actually the universe's way of maximizing entropy, or spreading out energy and information as evenly as possible. So, how does this connect to the missing energy problem? If gravity is tied to entropy and information, it could mean that the energy we're missing isn't actually gone. It's just distributed in ways we don't yet fully understand. For example, some of this energy might be stored in the fabric of spacetime itself, encoded in the way information is arranged across the universe. This could explain why our current measurements of energy don't add up, as we might not be accounting for this hidden, information-based energy. One of the most intriguing aspects of entropic gravity is how it bridges the gap between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. By framing gravity as an emergent property of information, entropic gravity offers a potential pathway to unifying these two frameworks, which could revolutionize our understanding of the cosmos. Of course, like any groundbreaking theory, entropic gravity has its skeptics. Critics argue that while the idea is elegant, it lacks direct experimental evidence. However, supporters point to its ability to explain phenomena like dark matter and dark energy without requiring new, exotic particles or forces. Instead, it suggests that the answers might lie in the way the universe processes and stores information. As we continue to explore the mysteries of the universe, entropic gravity reminds us that sometimes the most profound insights come from reimagining the most basic concepts. Next, we'll turn our attention to another fascinating piece of the puzzle: neutrinos, those elusive particles that might hold clues to the universe's missing energy. Stay with us as we uncover more layers of this cosmic enigma. Now, let's shift our focus to one of the most elusive particles in the universe: neutrinos. These ghostly particles are everywhere, streaming through space and even passing through you right now, yet they're incredibly difficult to detect. What makes neutrinos so fascinating, especially in the context of the universe's missing energy, is their tiny but non-zero mass. While they were once thought to be completely massless, we now know that neutrinos have a small amount of mass, and this discovery has profound implications for cosmology. Neutrinos are produced in vast quantities by stars, supernova, and even nuclear reactions here on Earth. Despite their abundance, they interact so weakly with matter that they can travel through entire planets without a single collision. This makes them incredibly hard to study, but their tiny mass means they could play a significant role in the universe's energy budget. Even though each neutrino has a mass that's almost unimaginably small, their sheer numbers mean they could collectively account for a portion of the missing energy we're trying to explain. So, how do neutrinos fit into cosmological models? In the early universe, neutrinos would have been moving at nearly the speed of light, behaving more like radiation than matter. But as the universe expanded and cooled, their speed slowed down, and they began to act more like particles with mass. This transition from radiation-like to matter-like behavior could have influenced the growth of large-scale structures like galaxies and galaxy clusters in ways that our current models might not fully capture. One intriguing possibility is that neutrinos could contribute to what we call hot dark matter. Unlike cold dark matter, which moves slowly and clumps together to form structures, hot dark matter moves quickly and tends to smooth out the distribution of matter in the universe. Neutrinos, with their small masses and high speeds, fit this description. While they likely don't make up all of the dark matter, they could still play a role in shaping the cosmos and explaining some of the missing energy. Another angle to consider is the neutrino's role in the cosmic microwave background, the afterglow of the Big Bang. The presence of neutrinos would have left subtle imprints on this ancient light, and by studying these imprints, scientists can infer properties like their mass and how they influenced the early universe. This connection between neutrinos and the cosmic microwave background provides another piece of the puzzle in understanding the universe's energy balance. While neutrinos alone may not solve the entire mystery of the missing energy, they remind us that even the smallest particles can have a big impact on the cosmos. Their tiny masses and elusive nature challenge our understanding of physics and push us to refine our models of the universe. As we continue to study these ghostly particles, we may uncover new clues that bring us closer to solving one of the greatest mysteries in science. Next, we'll explore another intriguing possibility: actions, hypothetical particles that could make up dark matter and contribute to the universe's missing energy. Stay tuned as we delve deeper into the cosmic enigma. Now, let's turn our attention to another fascinating candidate in the search for the universe's missing energy: actions. These hypothetical particles, first proposed in the late 1970s, have become a key focus in the quest to understand dark matter and the energy balance of the cosmos. Unlike neutrinos, which we know exist but are incredibly hard to pin down, actions remain purely theoretical, at least for now. But if they do exist, they could hold the key to solving some of the biggest mysteries in physics. Actions were originally introduced to solve a problem in particle physics known as the strong charge parity problem, which deals with the behavior of the strong nuclear force. But over time, scientists realized that actions could also be a perfect candidate for dark matter. These particles are predicted to be extremely light, possibly billions of times lighter than even the tiny neutrino, and they would interact so weakly with ordinary matter that they'd be nearly invisible to our detectors. This makes them incredibly difficult to detect, but their potential role in the universe's energy budget makes them worth the effort. One of the most intriguing properties of actions is how they could form a kind of invisible mist throughout the universe. Unlike other dark matter candidates, actions wouldn't clump together in the same way. Instead, they'd behave more like a smooth, pervasive field, filling the cosmos and subtly influencing its structure and evolution. This unique behavior could help explain why our observations of galaxies and galaxy clusters don't quite match our predictions based on visible matter alone. So, how do scientists search for something so elusive? One approach involves using powerful magnetic fields to try and convert actions into detectable photons. Experiments like the Action Dark Matter Experiment, or ADMX, use this method to scan for actions across a range of possible masses. Another strategy looks for actions produced in the Sun, hoping to catch a glimpse of these particles as they stream through space. While no definitive detection has been made yet, these experiments are steadily narrowing down the possibilities, bringing us closer to either confirming or ruling out the existence of actions. The search for actions isn't just about finding dark matter. It's also about testing the limits of our understanding of physics. If actions are discovered, they could provide answers to questions that go beyond the missing energy problem, shedding light on the fundamental nature of the universe itself. And even if they're never found, the pursuit of actions pushes the boundaries of experimental physics, driving innovation and inspiring new ways to explore the cosmos. As we continue to unravel the mysteries of the universe, actions remind us that sometimes the most elusive ideas can lead to the most profound discoveries. Next, we'll dive into another groundbreaking theory: supersymmetry, a framework that predicts partner particles for every known particle and could revolutionize our understanding of dark matter and missing energy. Stay with us as we explore this fascinating concept. Now, shifting our focus to another groundbreaking idea, let's explore supersymmetry, a theory that could fundamentally reshape our understanding of the universe. Supersymmetry, often abbreviated as SUSY, proposes a stunning symmetry between the two main classes of particles: fermions, which make up matter, and bosons, which carry forces. According to this theory, every known particle has a yet-to-be-discovered partner particle. For example, electrons would have counterparts called selectrons, and quarks would have squarks. This elegant framework doesn't just add new particles to the mix, it could also solve some of the most pressing mysteries in physics, including the nature of dark matter and the universe's missing energy. One of the most compelling aspects of supersymmetry is how it addresses the dark matter problem. The lightest of these hypothetical partner particles, often referred to as the lightest supersymmetric particle or LSP, could be stable and nearly invisible, making it a perfect candidate for dark matter. Unlike ordinary matter, these particles wouldn't interact strongly with light or other forms of electromagnetic radiation, which is why they've remained undetected so far. If supersymmetry is correct, the LSB could be the key to understanding why galaxies rotate faster than expected and why the universe's energy budget doesn't add up. But supersymmetry doesn't stop at dark matter. It also offers a potential explanation for the hierarchy problem in particle physics, which questions why the Higgs boson is so much lighter than the Planck scale, the energy level at which gravity becomes as strong as the other fundamental forces. Supersymmetry suggests that the Higgs boson's mass is kept in check by its superpartner, the Higgsino, effectively balancing the scales. This interplay between particles and their superpartners could provide a natural solution to one of the most puzzling aspects of the standard model of particle physics. Of course, the search for supersymmetry hasn't been easy. Despite decades of theoretical work and experimental efforts, including high-energy collisions at the Large Hadron Collider, no direct evidence of supersymmetric particles has been found yet. This has led some to question whether supersymmetry exists at all, or if it operates at energy scales far beyond our current reach. However, the absence of evidence isn't necessarily evidence of absence. Many physicists remain hopeful that future experiments with even greater precision and energy might finally uncover these elusive particles. Supersymmetry isn't just a scientific theory, it's a vision of a more unified and elegant universe. If proven true, it would not only explain dark matter and the missing energy, but also bridge gaps between quantum mechanics and general relativity, bringing us closer to a theory of everything. Even if supersymmetry isn't confirmed, the pursuit of it has already driven innovation in physics, pushing the boundaries of what we know and inspiring new ways to explore the cosmos. As we continue our journey through the theories of the universe's missing energy, let's turn our attention to another intriguing concept, the black hole information paradox. This mind-bending idea explores how black holes might hold clues to the universe's energy balance and how quantum effects could play a surprising role. Stay with us as we dive into this fascinating mystery. Now, let's venture into one of the most perplexing mysteries in modern physics, the black hole information paradox. This theory doesn't just challenge our understanding of black holes, it also raises profound questions about the universe's missing energy and the very nature of reality itself. At its core, the paradox revolves around a simple yet baffling question: what happens to information when it falls into a black hole? According to classical physics, once something crosses a black hole's event horizon, it's gone forever, lost to the universe. But quantum mechanics tells us that information can never truly be destroyed. This clash between two of science's most fundamental frameworks has left physicists scratching their heads for decades. The paradox becomes even more intriguing when we consider Hawking radiation, a phenomenon predicted by physicist Stephen Hawking. Black holes aren't entirely black. They emit tiny amounts of radiation over time, slowly losing mass and energy until they eventually evaporate. But here's the catch: Hawking radiation appears to be random, carrying no information about what fell into the black hole. If the black hole evaporates completely, where does all that information go? This is the heart of the paradox, a cosmic puzzle that seems to defy the laws of physics as we know them. Some scientists believe that resolving this paradox could shed light on the universe's missing energy. One possibility is that the information isn't truly lost but somehow encoded in the Hawking radiation itself, though in a form we don't yet understand. If this is the case, it could mean that black holes are not the ultimate cosmic trash cans but rather complex systems that preserve information in ways we're only beginning to grasp. This idea ties directly into the concept of quantum entanglement, where particles remain connected across vast distances, sharing information instantaneously. Could black holes be entangled with the radiation they emit, preserving the universe's energy balance in the process? Another fascinating angle is the idea of holography, where all the information about what falls into a black hole is stored on its surface or event horizon rather than inside it. This holographic principle suggests that the universe might operate like a giant hologram, with information encoded in 2 dimensions but appearing 3-dimensional to us. If true, this could mean that the missing energy isn't lost at all. It's just stored in a way we haven't yet figured out how to measure or observe. The black hole information paradox isn't just a theoretical curiosity. It's a gateway to understanding the deeper workings of the universe. By exploring how information and energy behave in the extreme environments of black holes, we might uncover clues about the missing energy that's baffled scientists for so long. Whether through Hawking radiation, quantum entanglement, or holography, the answers to this paradox could reshape our understanding of space, time, and the very fabric of reality. As we continue to unravel the mysteries of the cosmos, let's turn our attention to another captivating idea, the multiverse theory. Could the universe's missing energy be hiding in parallel worlds beyond our own? Stay with us as we explore this mind-expanding possibility. Now, let's take a leap into one of the most mind-bending ideas in modern cosmology, the multiverse theory. Imagine for a moment that our universe isn't the only one out there. Instead, it's just one of countless parallel universes, each with its own unique set of physical laws, constants, and even dimensions. This concept, while seemingly straight out of science fiction, is a serious area of study for physicists trying to solve the mystery of the universe's missing energy. If energy isn't disappearing from our universe, could it simply be leaking into or interacting with these other universes? The multiverse theory suggests that the total energy of all universes combined remains constant, even if energy appears to be missing in our own. Think of it like a cosmic balancing act. Energy might flow between universes through mechanisms we don't yet understand. For example, some theories propose the existence of brains or membranes in higher dimensional space. These brains could collide or interact, transferring energy between universes in ways that leave our own universe seemingly shortchanged. This idea ties into string theory, which suggests that our universe is just one layer in a much larger, multidimensional reality. Another intriguing possibility is that the missing energy in our universe is simply a result of how energy is distributed across the multiverse. If energy isn't evenly spread, some universes might have more while others have less. Our universe could be one of the less ones, giving the illusion that energy is missing when, in reality, it's just elsewhere. This idea challenges our understanding of conservation laws, suggesting that energy conservation might operate on a multiversal scale rather than a universal one. The multiverse theory also raises questions about the nature of dark energy. Could dark energy be a sign of interaction between our universe and others? Some scientists speculate that the accelerated expansion of our universe, driven by dark energy, might be influenced by the gravitational pull of neighboring universes. If true, this would mean that the missing energy problem isn't just about our universe, it's about the interconnectedness of all universes in the multiverse. While the multiverse theory is still speculative, it offers a fascinating framework for thinking about the universe's missing energy. It challenges us to expand our perspective beyond the confines of our own universe and consider the possibility that the answers we're seeking might lie in realms we can't yet observe or measure. Whether through brains, energy redistribution, or interactions between universes, the multiverse theory opens up a universe of possibilities, literally. As we ponder the idea of parallel worlds, let's shift our focus to another intriguing concept: time-varying constants. Could the fundamental laws of physics themselves be changing over time, affecting how we perceive the universe's energy? Stay with us as we explore this thought-provoking theory next. Now, let's turn our attention to a theory that challenges one of the most fundamental assumptions in physics, the idea that the laws of the universe are fixed and unchanging. What if the constants we rely on to understand the cosmos, like the gravitational constant or the speed of light, aren't as constant as we think? This is the essence of the time-varying constants theory, a concept that could reshape our understanding of the universe's missing energy. At the heart of this theory is the possibility that the fundamental constants of nature might not be constant at all. Instead, they could change over time, subtly altering the way energy behaves and is distributed throughout the universe. For example, if the gravitational constant, which determines the strength of gravity, were to decrease over billions of years, it could affect how galaxies form, how stars burn, and even how the universe expands. These changes might create discrepancies in our energy calculations, making it seem like energy is missing when, in reality, our understanding of the constants is incomplete. One of the most intriguing aspects of this theory is how it connects to the early universe. During the first moments after the Big Bang, the universe was a hot, dense soup of particles and energy. If the fundamental constants were different back then, even by a tiny amount, it could have had a profound impact on how the universe evolved. For instance, a slightly stronger gravitational constant in the early universe might have led to faster star formation, altering the distribution of energy we observe today. This could explain why our current measurements of the universe's energy don't add up, because we're using constants that might not have always been the same. But how could constants change over time? Some theories suggest that these changes might be tied to the expansion of the universe itself. As space stretches, the fabric of reality might subtly shift, causing constants to drift. Others propose that these variations could be linked to deeper, yet to be discovered laws of physics, such as those involving extra dimensions or quantum gravity. While these ideas are still speculative, they offer a compelling way to rethink the missing energy problem. The implications of time-varying constants are profound. If true, it would mean that the laws of physics aren't as universal or timeless as we once thought. Instead, they could be dynamic, evolving alongside the universe itself. This would not only challenge our understanding of energy, but also force us to reconsider how we model the cosmos. It's a reminder that the universe is full of surprises, and sometimes the answers we're looking for might lie in questioning the very foundations of what we know. As we explore this fascinating idea, let's move on to another theory that takes us even deeper into the fabric of reality: emergent gravity. Could gravity itself be an illusion, emerging from something even more fundamental? Stay with us as we dive into this next intriguing concept. Now, let's shift our focus to a theory that turns our understanding of gravity on its head: emergent gravity. What if gravity isn't a fundamental force at all, but something that emerges from the collective behavior of tiny, underlying components of the universe? This is the core idea behind emergent gravity, a concept that could offer a fresh perspective on the mystery of the universe's missing energy. Emergent gravity suggests that what we perceive as gravity might not be a fundamental force like electromagnetism or the strong nuclear force. Instead, it could arise from the interactions of microscopic degrees of freedom, tiny, fundamental building blocks of spacetime itself. Think of it like the way temperature emerges from the motion of countless molecules in a gas. You don't see the individual molecules, but their collective behavior gives rise to something we can measure and feel. In the same way, gravity might be an emergent phenomenon, a byproduct of deeper, hidden processes in the fabric of reality. One of the most compelling aspects of this theory is how it challenges the need for dark matter. If gravity emerges from these microscopic interactions, it could explain the observed gravitational effects in galaxies and galaxy clusters without invoking invisible, mysterious particles. For example, the way stars orbit the centers of galaxies or how galaxy clusters hold together could be the result of emergent gravity, not the presence of dark matter. This would mean that the missing energy problem might not be about finding unseen matter, but about understanding how gravity truly works on cosmic scales. The idea of emergent gravity also ties into some of the most cutting-edge areas of physics, like quantum mechanics and string theory. Some researchers propose that space-time itself might be made up of tiny, discrete units like pixels on a screen, and that gravity emerges from the way these units interact. This could open up new ways to think about the universe's energy budget, as the behavior of these microscopic components might hold the key to explaining why our current calculations don't add up. Of course, emergent gravity is still a speculative theory, and it faces significant challenges. For one, it's difficult to test experimentally, as the microscopic degrees of freedom it relies on are far beyond our current ability to observe. Additionally, it requires a radical rethinking of some of the most well-established principles in physics, like Einstein's theory of general relativity. But that's what makes it so exciting. It pushes the boundaries of our understanding and invites us to consider entirely new possibilities. As we wrap up this exploration of emergent gravity, let's turn our attention to another fascinating idea: loop quantum gravity. Could the universe's missing energy be tied to the way space-time is woven together at the smallest scales? Stay with us as we dive into this next intriguing theory. Now, let's venture into the realm of loop quantum gravity, a theory that seeks to bridge two of the most profound pillars of modern physics: quantum mechanics and general relativity. What if the universe's missing energy is hidden in the very fabric of space-time itself, woven together in ways we're only beginning to understand? Loop quantum gravity offers a bold and imaginative answer to this question, proposing that space-time is not smooth and continuous as Einstein described, but rather made up of tiny, discrete loops. At its core, loop quantum gravity suggests that space-time is quantized, meaning it's composed of finite, indivisible units. Imagine space-time as a fabric stitched together from countless tiny loops, each representing the smallest possible piece of reality. These loops form a network, creating the structure of the universe at the most fundamental level. This idea challenges our classical understanding of space-time and opens up new possibilities for explaining the universe's missing energy. One of the most intriguing aspects of loop quantum gravity is how it addresses the singularity problem, the point in black holes or the Big Bang where classical physics breaks down. In this theory, singularities don't exist because space-time can't be compressed infinitely. Instead, the loops prevent space-time from collapsing into a single point, offering a way to avoid the infinite densities and energies that classical theories predict. This could mean that the universe's missing energy is tied to the way these loops interact and evolve over time. Another fascinating implication of loop quantum gravity is its potential to explain dark energy. If space-time is made up of these discrete loops, their behavior at the smallest scales might influence the large-scale structure of the universe. Some researchers suggest that the energy associated with these loops could contribute to the accelerated expansion of the universe, providing a natural explanation for dark energy without the need for additional exotic components. However, like many groundbreaking theories, loop quantum gravity faces its share of challenges. For one, it's incredibly difficult to test experimentally, as the scales involved are far beyond what we can currently observe. Additionally, the mathematics behind the theory is highly complex, making it a daunting task even for seasoned physicists. But despite these hurdles, loop quantum gravity remains a promising avenue for exploring the deepest mysteries of the cosmos. As we wrap up this exploration of loop quantum gravity, let's turn our attention to another captivating idea: Kaluza-Klein theory. Could the universe's missing energy be hiding in dimensions beyond the ones we experience every day? Stay with us as we uncover this next intriguing possibility. Now, let's take a step into the fascinating world of Kaluza-Klein theory, a concept that dares to imagine our universe in ways that stretch beyond the three dimensions we know. What if the universe's missing energy isn't lost at all, but simply tucked away in a dimension we can't see? Kaluza-Klein theory offers a bold and elegant framework that not only unifies gravity and electromagnetism, but also opens the door to explaining the mystery of missing energy through the existence of extra dimensions. At its heart, Kaluza-Klein theory proposes that our universe might have more than just the three spatial dimensions of length, width, and height. In the early 20th century, mathematician Theodore Kaluza and physicist Oskar Klein suggested that adding a fourth spatial dimension could elegantly combine Einstein's theory of general relativity, which describes gravity, with Maxwell's equations of electromagnetism. This extra dimension, though hidden from our everyday perception, could hold the key to understanding the universe's missing energy. Here's how it works. Imagine the extra dimension as a tiny, curled-up loop so small that it's invisible to us. Just as a garden hose looks like a one-dimensional line from a distance but reveals its circular shape up close, this extra dimension might be compactified or tightly wound at scales far smaller than we can detect. The energy associated with this hidden dimension could manifest in ways that influence the behavior of the universe on larger scales, potentially accounting for the missing energy we observe. One of the most intriguing aspects of Kaluza-Klein theory is how it connects the forces of nature. In this framework, electromagnetism emerges as a byproduct of gravity operating in the extra dimension. This unification not only simplifies our understanding of the fundamental forces, but also suggests that the missing energy could be tied to the dynamics of these higher dimensional interactions. If energy is distributed across multiple dimensions, some of it might simply be hidden from our three-dimensional perspective. But how does this relate to the universe's missing energy? Some physicists speculate that the energy associated with the vibrations or excitations of particles in the extra dimension could contribute to the total energy budget of the universe. These vibrations, often referred to as Kaluza-Klein modes, might carry energy that doesn't directly interact with our three-dimensional world, but still influences the overall structure and expansion of the cosmos. This could provide a natural explanation for phenomena like dark energy, without the need for entirely new forms of matter or energy. Of course, Kaluza-Klein theory isn't without its challenges. Detecting an extra dimension, if it exists, would require experiments far beyond our current technological capabilities. Additionally, the theory raises questions about why we perceive only three spatial dimensions and how the extra dimension remains so tightly curled. Despite these hurdles, Kaluza-Klein theory remains a compelling and imaginative approach to unifying the forces of nature and addressing the mystery of the universe's missing energy. As we leave the realm of extra dimensions behind, let's turn our attention to another intriguing idea: tachyonic fields. Could particles that move faster than light hold the answer to the universe's missing energy? Stay with us as we explore this next fascinating possibility. Now, let's venture into the realm of the extraordinary tachyonic fields. These hypothetical fields are unlike anything we've discussed so far, and they challenge our understanding of mass, energy, and even the speed of light. What if the universe's missing energy isn't tied to something we can observe or measure directly, but instead to particles that defy the very laws of physics as we know them? That's where tachyonic fields come into play. Tachyonic fields are theorized to involve particles with imaginary mass, a concept that might sound straight out of science fiction. In physics, imaginary mass doesn't mean the mass is fake or non-existent. It's a mathematical way of describing particles that could travel faster than light. These hypothetical particles, known as tachyons, would exist in a state where their speed exceeds the cosmic speed limit set by light. But how does this connect to the universe's missing energy? The idea is that tachyonic fields could influence the fabric of spacetime in ways that aren't immediately obvious. If these fields exist, they might create fluctuations or disturbances in the energy of the universe, contributing to the overall energy budget in ways we can't directly detect. Some theories suggest that tachyonic fields could act as a kind of background energy, subtly shaping the expansion and structure of the cosmos. This energy, though hidden, might be the key to explaining why our observations of the universe's energy don't add up. One of the most fascinating aspects of tachyonic fields is their potential to explain phenomena like dark energy. If these fields are real, their energy could permeate the universe, driving its accelerated expansion without the need for dark energy as a separate entity. This would offer a unified explanation for both the missing energy and the mysterious force pushing galaxies apart. However, the concept of tachyons comes with its own set of challenges. For one, particles moving faster than light would violate causality, the principle that cause precedes effect. This raises questions about how such particles could exist without creating paradoxes in our understanding of time and space. Despite these challenges, tachyonic fields remain a captivating area of theoretical exploration. They push the boundaries of our knowledge and invite us to consider possibilities that lie beyond the limits of current physics. While we have no direct evidence for tachyons or their associated fields, their potential to explain the universe's missing energy keeps them in the conversation as one of the many intriguing theories scientists are investigating. As we move forward, let's shift our focus to another compelling idea: non-local gravity. Could the way gravity operates across vast distances hold clues to the universe's missing energy? Stay with us as we dive into this next fascinating theory. Now, let's turn our attention to a theory that reimagines one of the most fundamental forces in the universe: gravity. Non-local gravity proposes that the effects of gravity aren't confined to the immediate vicinity of massive objects, but instead extend far beyond, influencing regions of space that seem disconnected from the source. This idea challenges the traditional view of gravity as a purely local force and opens up new possibilities for understanding the universe's missing energy. In classical physics, gravity is described by Einstein's theory of general relativity, which treats it as a curvature of spacetime caused by mass and energy. This curvature is local, meaning it's strongest near massive objects like stars and planets and weakens as you move away. But what if gravity's influence isn't limited to these local regions? Non-local gravity suggests that gravitational effects can propagate across vast distances, creating connections between seemingly unrelated parts of the universe. This could mean that energy, too, isn't confined to where we expect it to be. One way non-local gravity might account for the universe's missing energy is by redistributing it across space. If gravity operates non-locally, it could transfer energy from one region to another, effectively hiding it from our observations. For example, energy that appears to be missing in our local universe might actually be spread out across distant regions, tied together by the non-local gravitational interactions. This would mean that the energy isn't truly gone, it's just not where we're looking. Another intriguing aspect of non-local gravity is its potential to explain phenomena like dark energy. If gravity's influence extends beyond local regions, it could create a kind of background energy field that permeates the entire universe. This field might drive the accelerated expansion of the cosmos, mimicking the effects of dark energy without requiring an entirely new form of energy. In this way, non-local gravity could offer a unified explanation for both the missing energy and the mysterious force pushing galaxies apart. However, non-local gravity isn't without its challenges. For one, it requires a significant departure from our current understanding of physics, particularly general relativity. It also raises questions about how such long-range gravitational interactions would work in practice and how they could be tested or observed. Despite these hurdles, the theory remains a compelling area of research, offering a fresh perspective on one of the universe's greatest mysteries. As we continue our exploration, let's shift our focus to another fascinating concept: vacuum decay. Could the universe's missing energy be tied to a fundamental shift in the fabric of reality itself? Stay with us as we delve into this next intriguing theory. Now, let's venture into a theory that feels like it's straight out of a science fiction novel: vacuum decay. Imagine the universe as a vast, intricate structure, but what if this structure isn't as stable as we think? Vacuum decay suggests that the universe could undergo a dramatic shift, transitioning from its current state to a lower energy one. This process, while sounding almost apocalyptic, might hold the key to understanding the universe's missing energy. To grasp this idea, let's start with the concept of the vacuum itself. In physics, a vacuum isn't just empty space, it's a state of minimal energy, but not necessarily zero energy. Think of it like a valley surrounded by hills. The universe, in its current state, sits in a stable valley, but there might be a deeper, more stable valley nearby. If the universe were to roll into this lower valley, it would release energy in the process, potentially explaining where some of the missing energy has gone. This transition, known as vacuum decay, could happen if a tiny region of the universe were to suddenly shift to this lower energy state. This region would act like a bubble, expanding at the speed of light and rewriting the fundamental laws of physics as it grows. While this might sound catastrophic, it's important to note that such an event is purely hypothetical, at least for now. But if it were to occur, the energy released during this transition could account for some of the universe's missing energy. One of the most fascinating aspects of vacuum decay is its connection to the Higgs field, the quantum field responsible for giving particles their mass. The Higgs field exists in a particular energy state, but if it were to drop to a lower state, it could trigger vacuum decay. This would not only release energy, but also alter the very fabric of reality, changing the properties of particles and forces in ways we can't fully predict. So how does this tie into the missing energy problem? If vacuum decay were to occur, even on a small scale, it could redistribute energy across the universe, effectively hiding it from our observations. This energy wouldn't be destroyed, it would simply be transformed into a form we can't easily detect. It's a bit like losing your keys in a different room. They're still there, just not where you're looking. Of course, vacuum decay is still a speculative idea, and there's no direct evidence that it's happening or has ever happened. But it's a compelling theory that challenges our understanding of the universe's stability and energy distribution. As we continue to explore the cosmos, theories like this remind us just how much we still have to learn. With that in mind, let's move on to another captivating idea: cosmic inflation. Could the universe's rapid expansion shortly after the Big Bang have left behind energy that we're still searching for today? Let's find out. Now, let's turn our attention to one of the most groundbreaking ideas in modern cosmology: cosmic inflation. Picture this: in the tiniest fraction of a second after the Big Bang, the universe didn't just expand, it exploded outward at an unimaginable speed, stretching space itself faster than the speed of light. This rapid expansion, known as cosmic inflation, might hold the key to understanding where some of the universe's missing energy has gone. To understand cosmic inflation, let's start with the Big Bang. Most of us think of the Big Bang as a massive explosion, but it wasn't just an explosion of matter. It was an explosion of space itself. In the earliest moments, the universe was incredibly hot and dense, and then suddenly it underwent a period of exponential growth. This wasn't just a gentle expansion, it was a dramatic stretching of the fabric of space-time, doubling in size over and over again in the blink of an eye. But why does this matter for the missing energy problem? Well, during this rapid expansion, the universe was filled with a kind of energy field, often called the inflaton field, that drove the process. As the universe expanded, this field released energy, which eventually settled into the particles and forces we see today. However, some of that energy might have been locked away in ways we can't easily detect. Think of it like blowing up a balloon. As it expands, the surface stretches, and some of the energy used to inflate it becomes part of the balloon's structure, hidden from view. One of the most intriguing aspects of cosmic inflation is that it could explain why the universe looks so uniform on large scales. The rapid expansion would have smoothed out any irregularities, creating the even distribution of matter and energy we observe today. But it also raises questions. If inflation stretched space so dramatically, could it have stretched energy as well, making it harder for us to detect? Some scientists believe that the energy released during inflation might have been redistributed in ways that leave traces we're still searching for. Another fascinating possibility is that inflation didn't just happen once. It could have happened in multiple regions of the universe, creating a kind of multiverse where each region has its own unique properties. In this scenario, the energy we're missing in our observable universe might simply be part of a larger, more complex cosmic picture. It's like trying to understand a single puzzle piece without seeing the entire puzzle. While cosmic inflation is widely accepted as a leading explanation for the universe's early expansion, it's not without its challenges. For one, we don't yet have direct evidence of the inflattened field or the exact mechanisms that drove inflation. But the theory has made predictions that align remarkably well with observations, such as the cosmic microwave background radiation, the faint afterglow of the Big Bang. So, could cosmic inflation be the answer to the missing energy mystery? It's a compelling possibility. By stretching space and redistributing energy in ways we're still uncovering, inflation might have left behind clues that we're only beginning to understand. As we continue to explore the universe's earliest moments, theories like this remind us just how much there is to discover. With that in mind, let's shift our focus to another intriguing idea: gravitational waves. Could these ripples in space-time carry away energy, contributing to the universe's missing energy problem? Let's explore this next. Now, let's dive into another fascinating piece of the cosmic puzzle: gravitational waves. These ripples in space-time, first predicted by Albert Einstein over a century ago, have opened up a whole new way of observing the universe. But could they also hold clues to the mystery of the universe's missing energy? Let's find out. Gravitational waves are created by some of the most violent and energetic events in the cosmos: colliding black holes, merging neutron stars, and even the explosive birth of the universe itself. When these massive objects move or collide, they send out waves that stretch and squeeze space-time itself, much like ripples spreading across the surface of a pond. These waves carry energy with them, energy that travels across the universe at the speed of light. But here's where things get interesting. When gravitational waves are emitted, they carry away energy from the system that created them. For example, when two black holes spiral toward each other and merge, a significant amount of energy is radiated away in the form of gravitational waves. This energy doesn't just disappear, it's transferred out into the universe, spreading far and wide. Over billions of years, countless such events could have contributed to a vast reservoir of energy that's now missing from our observable universe. One of the key questions is whether this energy could be part of the dark energy driving the universe's accelerated expansion. While gravitational waves themselves don't directly explain dark energy, they do offer a way to understand how energy can be redistributed on cosmic scales. Think of it like this: if the universe is a giant ocean, gravitational waves are the ripples that carry energy from one place to another, potentially hiding it in ways we're still trying to uncover. Another intriguing possibility is that gravitational waves could interact with other forms of energy in ways we don't yet fully understand. For instance, some theories suggest that gravitational waves might influence the behavior of dark matter or even the fabric of space-time itself. If true, this could mean that the energy carried by gravitational waves plays a more significant role in the universe's overall energy budget than we currently realize. The detection of gravitational waves in recent years has been a game changer for cosmology. Thanks to observatories like LIGO and Virgo, we've been able to listen to the universe in a whole new way, picking up the faint echoes of distant cosmic collisions. Each detection not only confirms Einstein's predictions, but also provides new data that could help us piece together the puzzle of the universe's missing energy. So, could gravitational waves be hiding some of the energy we're searching for? It's a tantalizing idea. While they may not be the sole explanation, they certainly add another layer to the mystery, reminding us that the universe is full of surprises. As we continue to study these ripples in space-time, who knows what other secrets they might reveal? With that in mind, let's turn our attention to another intriguing possibility: primordial black holes. Could these ancient remnants from the early universe hold the key to the missing energy problem? Let's explore this next. Now, let's shift our gaze to the early universe, where another intriguing possibility emerges: primordial black holes. These hypothetical objects, thought to have formed in the first moments after the Big Bang, could hold clues to the mystery of the universe's missing energy. But what exactly are primordial black holes, and how might they fit into this cosmic puzzle? Unlike the black holes we're familiar with, which form from the collapse of massive stars, primordial black holes are believed to have originated from extreme density fluctuations in the early universe. Imagine the universe as a bubbling cauldron of energy and matter, where tiny regions of space became so dense that they collapsed under their own gravity, forming black holes. These ancient objects could range in size from as small as an atom to as massive as a star, and they might still exist today, scattered throughout the cosmos. One of the most fascinating aspects of primordial black holes is their potential to account for some of the universe's missing energy. If they exist in large numbers, their collective gravitational influence could explain why we observe less energy in the universe than our models predict. Think of it like this: if primordial black holes are hiding in the shadows, their gravitational pull could be subtly shaping the behavior of galaxies and galaxy clusters, effectively masking the energy we're searching for. But how could these ancient black holes contribute to the missing energy problem? One possibility is that they could be a form of dark matter. While we typically think of dark matter as a mysterious, invisible substance, primordial black holes could fit the bill. Their gravitational effects would be similar to those of dark matter, influencing the motion of stars and galaxies without emitting any light. If a significant portion of dark matter is made up of primordial black holes, it would mean that the universe's missing energy is in part tied up in these ancient objects. Another intriguing idea is that primordial black holes could interact with other forms of energy in ways we don't yet fully understand. For instance, some theories suggest that they might emit radiation over time through a process known as Hawking radiation, slowly losing mass and energy. If this is the case, primordial black holes could be releasing energy back into the universe, contributing to the overall energy budget in subtle but significant ways. The search for primordial black holes is still ongoing, with scientists using a variety of methods to detect their presence. From gravitational lensing, where their gravity bends light from distant stars, to the study of cosmic microwave background radiation, researchers are exploring every possible avenue to uncover these elusive objects. While we haven't found definitive evidence yet, the possibility remains tantalizing. So, could primordial black holes be the key to solving the mystery of the universe's missing energy? While they may not provide the full answer, they certainly add another layer to the puzzle, reminding us that the early universe was a place of incredible complexity and potential. As we continue to explore these ancient relics, who knows what other secrets they might reveal? With that in mind, let's turn our attention to another fascinating idea: exotic matter. Could this hypothetical form of matter, with its unusual properties, hold the key to the missing energy problem? Let's dive in and find out. Now, let's venture into the realm of the truly extraordinary exotic matter. This isn't your everyday, run-of-the-mill material. Exotic matter refers to hypothetical particles and substances that defy the usual rules of physics, possessing properties that seem almost magical. But could these strange forms of matter hold the key to the universe's missing energy? Let's explore this intriguing possibility. Exotic matter is a broad term that encompasses a variety of theoretical particles and states of matter. Unlike ordinary matter, which is made up of protons, neutrons, and electrons, exotic matter could include particles with negative mass, faster-than-light capabilities, or even the ability to warp spacetime itself. These unusual properties make exotic matter a fascinating candidate for explaining some of the universe's most puzzling mysteries, including the missing energy problem. One of the most well-known examples of exotic matter is negative mass. Imagine a substance that, instead of being pulled by gravity, is pushed away. Negative mass would have the opposite effect of regular matter, creating repulsive gravitational forces. While this might sound like science fiction, some theories suggest that negative mass could exist in the universe, potentially influencing the behavior of galaxies and the expansion of space itself. If exotic matter with negative mass is out there, it could be contributing to the universe's missing energy in ways we're only beginning to understand. Another intriguing idea is that exotic matter could be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories propose that exotic particles with unusual energy properties could be the source of dark energy, filling the cosmos with a kind of anti-gravity that pushes galaxies apart. If this is the case, exotic matter wouldn't just be a curiosity, it would be a fundamental component of the universe's energy balance. But how could we detect something so strange and elusive? The search for exotic matter is still in its early stages, with scientists relying on indirect methods to look for its effects. For example, some researchers are studying the behavior of light as it travels through space, searching for distortions that could hint at the presence of exotic particles. Others are exploring the possibility of creating exotic matter in laboratories, using powerful particle accelerators to probe the boundaries of known physics. While the existence of exotic matter remains unproven, its potential to explain the universe's missing energy is undeniable. Whether it's through negative mass, dark energy, or some other yet-to-be-discovered property, exotic matter offers a tantalizing glimpse into the hidden workings of the cosmos. As we continue to push the boundaries of our understanding, who knows what other extraordinary discoveries might be waiting just beyond the horizon? With that in mind, let's turn our attention to one final theory, the anthropic principle. Could the universe's missing energy be a result of the very conditions that allow us to exist? Let's dive into this thought-provoking idea next. Now, let's take a step back and consider a completely different perspective, one that shifts the focus from the physical to the philosophical. The anthropic principle offers a unique lens through which to view the universe's missing energy, suggesting that the very conditions we observe might be intricately tied to the existence of life itself. Could it be that the universe's missing energy isn't a mystery to be solved, but rather a necessary feature of a cosmos fine-tuned for beings like us? The anthropic principle comes in two main forms, the weak and the strong. The weak anthropic principle simply states that the conditions we observe in the universe must be compatible with the existence of observers, us. In other words, if the universe didn't have the properties it does, we wouldn't be here to question them. This might seem obvious, but it raises an intriguing point. The universe's missing energy could be a consequence of the specific balance required for life to emerge. If the energy distribution were different, stars, planets, and ultimately life might never have formed. The strong anthropic principle takes this idea a step further, proposing that the universe must have properties that allow life to develop. This version of the principle suggests a kind of cosmic fine-tuning, where the fundamental constants and laws of physics are precisely calibrated to create a universe capable of supporting life. From this perspective, the missing energy isn't an anomaly, it's a necessary part of the equation. Without it, the universe might lack the stability or structure needed for life to exist. But how does this relate to the missing energy problem? One possibility is that the energy we perceive as missing is actually tied to the conditions that make life possible. For example, the accelerated expansion of the universe driven by dark energy might be essential for creating the vast, structured cosmos we inhabit. If the universe were static or collapsing, it's unlikely that galaxies, stars, and planets would form in the way they have. In this sense, the missing energy could be seen as a byproduct of a universe designed, or at least suited, for life. Of course, the anthropic principle doesn't provide a definitive answer to the missing energy problem. Instead, it offers a thought-provoking framework for understanding why the universe might be the way it is. It challenges us to consider not just how the universe works, but why it works in a way that allows us to exist. This principle doesn't replace the need for scientific investigation, but it does remind us that our search for answers is deeply intertwined with our own existence. As we wrap up our exploration of the universe's missing energy, it's worth reflecting on the incredible diversity of ideas we've encountered. From dark matter and dark energy to exotic particles and cosmic fine-tuning, each theory offers a unique perspective on one of the greatest mysteries in science. While we may not have all the answers yet, the journey of discovery is as fascinating as the destination. And with that, we've reached the end of our cosmic exploration. If you've enjoyed this deep dive into the universe's missing energy, don't forget to like, subscribe, and hit the notification bell for more mind-bending mysteries. Until next time, keep looking up, there's always more to discover. As we bring our journey through the cosmos to a close, let's take a moment to reflect on the incredible array of theories we've explored. From the enigmatic presence of dark matter and dark energy to the mind-bending possibilities of extra dimensions and cosmic strings, each idea offers a unique lens through which to view the universe's missing energy. Whether it's the subtle influence of neutrinos, the speculative nature of phantom energy, or the philosophical implications of the anthropic principle, one thing is clear: the mystery of the universe's missing energy is as vast and complex as the cosmos itself. What's truly remarkable is the diversity of thought behind these theories. Scientists, philosophers, and thinkers from across disciplines have come together to tackle this profound question, each bringing their own perspective and expertise. Some theories rely on the unseen, like dark matter and actions, while others challenge our fundamental understanding of physics, such as modified gravity or the holographic principle. And then there are those that push the boundaries of imagination, like the multiverse or vacuum decay. Together, they paint a picture of a universe that is far stranger and more fascinating than we could have ever imagined. But here's the thing: the search for answers is far from over. Each theory we've discussed is a piece of a much larger puzzle, and while we may not have all the pieces yet, the process of discovery is what makes science so thrilling. Every observation, every experiment, and every new idea brings us one step closer to understanding the true nature of the cosmos. And who knows, the next breakthrough could come from you. If you've enjoyed this exploration of the universe's greatest mysteries, don't forget to share your thoughts in the comments below. Which theory do you find the most compelling? Or do you have your own ideas about where the missing energy might be hiding? Let's keep the conversation going. And if you're hungry for more cosmic mysteries, hit that subscribe button and ring the notification bell so you never miss an update. Thank you for joining me on this journey through the stars. Until next time, keep wondering, keep exploring, and remember, the universe is full of secrets waiting to be uncovered. See you in the next video.